In this video, we'll talk about how to analyze quantitative data when we're comparing more than two groups. We've previously seen how to use t-tests to compare two groups with quantitative data, and now we'll extend this to a more general ANOVA F test to test for differences when we have more than two groups. In the video, we'll talk about how to use the ANOVA F test to test for differences in means for quantitative data involving multiple groups, how to determine whether it's appropriate to use an ANOVA F test in a given context, how to interpret the results of an ANOVA F test, and how to use pairwise t-tests with Bonferroni correction to test for differences between groups. We'll use an example that's referenced in the textbook Statistics Unlocking the Power of Data by the Locke family. In this study, researchers are interested in studying how exposure to light at night impacted weight gain in mice. In an experiment, 27 mice were randomly assigned to one of three light conditions. One group of mice was kept in standard light conditions during the day and in dark at night. Another was kept in bright light at all times. The third was kept in dim light at night and regular light during the day. After 3 weeks, the researchers recorded the body mass gain in grams in each of the mice. We want to test whether there are differences in mean weight gain for the three different light cycles. Our null hypothesis will be that there is no difference between the settings, that is, the mean weight gain is the same for each light-dark setting over all mice. The alternative hypothesis is that the mean weight gain is different for at least one of the settings. In this situation, we have numerical data. We're measuring body mass gain in grams. So the chi-square tests we discussed in the previous video, which pertain to categorical data, won't work here. Instead, we'll use a procedure known as analysis of variance, which is often abbreviated ANOVA. An ANOVA F test is appropriate in situations where we have quantitative data, provided that our observations are independent, data within each group are approximately normally distributed, and variability is roughly equal between the groups. Let's take a look at the data for the mice. In the table, we see the mean weight gain for the mice in each category. So for the mice that were kept in dim light, they gained about 7.86 grams over the 3 weeks in the study. The mice that were kept in the standard light-dark cycle gained about 5.9 grams, and the mice that were kept in light all the time gained an average of 11 grams. You can also see the standard deviation for each group and the number of mice in each setting, as well as a box plot that demonstrates these differences. It looks like the mice being kept in the light all the time seem to be perhaps gaining more weight than the other mice, followed by the mice kept in dim lighting, and then the mice kept in the standard light-dark cycle. But the question is, are these differences significant? Could we have just observed differences between the groups this big by pure chance? We'll investigate that using an ANOVA F test. An F test compares the amount of variability within each group to the amount of variability between the different groups. To illustrate what the F test does, we have two different plots, and these don't pertain to the mice data. These are merely examples of comparisons of three different groups. In the first scenario, shown on the left, we have three groups, A, B, and C, shown on the x-axis. And you can see the response. You could think about it as weight gain or whatever we're measuring for the three groups seems to be different. In particular, group B seems to be quite a bit higher than groups A and C. And we also observe there's quite a bit of consistency within each group. All of the observations for B are pretty close together. All of the observations for A are pretty close together. Same thing with C. There's a lot of variability between the groups. B is quite a bit different than C and A, but there's not a lot of variability within the groups. A picture like this provides strong evidence that there are true differences between the groups. On the other hand, in scenario 2, shown on the right, we see that the groups don't look that different. The points seem to be scattered more without a clear sign that one group is much bigger or smaller than the rest. And even within each group, the points are much more scattered out as opposed to being clustered closely together over in scenario 1. In scenario 2, the variability between the groups is small, but the variability within each group is large. This suggests that there's not a lot of evidence of differences between groups A, B, and C. To recap, when we have high variability between groups and low variability within groups, that provides strong evidence of differences in the means between groups. In that situation, the F statistic we'll calculate will be large. When we have little variability between the groups, but a lot of variability within the groups, then we don't really have evidence of differences, and the F statistic we calculate will be small. Let's use R to calculate the F statistic in the mice example. We do that using the AOV command. We obtain an F statistic, which is shown in the third column of our table, of 8.385, and a p-value of 0.00173. If we graph where that F statistic falls on an F distribution, we see that it lies way out in the tail, far away from where most of the distribution lies. This indicates that our result is very extreme and is not consistent with what we would have expected to see if the null hypothesis was true. That is, if there really was no difference in mean weight gain between the groups, the light settings. Thus, we have evidence to conclude that there are differences in mean body mass gain in mice between the different light-dark settings. We don't know, however, whether there's evidence of which settings differ from one another. Are all three different? Is it just that one is different than the other two? We still need to investigate that, and we can compare individual settings using t-tests as we've seen before. So in this case, we'll compare the light-dark setting to the dim light setting and also to the light-light setting, plus compare the dim light setting to the light-light setting. We have three different comparisons that we need to make, and we can do that using the pairwise t-test in R. The command is pairwise t-test, and what we see is a table that compares the different groups, and the values you see within the table are p-values for testing the null hypothesis that there is no difference between the groups. So in this first cell in the table, I see a p-value of 0.12972, which corresponds to a test for whether there are differences between the light-dark setting, the standard setting, and the dim-light setting. The fact that the p-value is relatively large, it's bigger than 0.1, tells us that we don't have evidence to conclude that there are differences between the standard setting and the dim light setting. In the next row, we have comparisons between the light setting, so the mice who were kept in bright light all the time, and each of the other two, the dim light setting and the light dark setting. We see that both of those p-values are smaller, certainly less than 0.05. Now, before we draw conclusions, we need to think about the fact that we're using three different tests here. And we've talked before about how when you do multiple tests at the same time, sometimes you'll expect some of them to get small p-values just by chance alone. So a correction we can use in this situation is the Bonferroni correction, which says that rather than using 0.05 as a cutoff, divide that by the number of different comparisons we're making. In this case, we're making 3 different comparisons. So let's divide 0.05 by 3, and that gives us a cutoff of 0.0167. Thus, using the Bonferroni correction, we should only reject the null hypothesis and conclude that there are differences between groups if we get p-values less than 0.0167. In this case, both of the p-values in the lower row, comparing the bright light setting to the other two, are still less than that cutoff. So we still have evidence that there are differences in weight gain between the light setting compared to each of the other two conditions. In particular, mice are gaining more weight on average when they're kept in light all the time than when they're being kept in darkness or dim light at night. However, we don't have evidence to conclude that there are differences in weight gain between the dim light and the light-dark settings. To recap, in this video, we've discussed how to use the ANOVA F test to test for differences in means for quantitative data with multiple groups, how to determine whether it's appropriate to use an ANOVA F test in a given context, how to interpret the results of an ANOVA F test, and how to use pairwise t-tests with Bonferroni correction to test for differences between groups.